Hello everybody, and welcome to our lecture on projections and datums. And this is one of my favorite topics in GIS. Once you understand what these things mean and how to use them, you'll find they're really a lot of fun to play with, and you can use them to create some really interesting cartographic effects. So what are they? Why do we care? Projections are an extremely important part of GIS, and we have to understand them. They are an integral part of spatial data. We cannot avoid dealing with them. Just the simple fact that the data are spatial means they have to have some sort of coordinates that locate them in space, and this implies some coordinate system that they exist in. Now, on a simple level, projections affect the visual quality of our maps, and on a deeper level, they affect our analysis by changing the actual sizes and shapes of the things we're analyzing. Projections can make it easy or impossible to find locations on the ground when you're out in the field. Unfortunately, they can be confusing, and in fact, people who have been doing GIS for years can have trouble with them, especially with datums. Many people just never learned how to work with data that lie on different lat-long systems. Many people don't realize there are different latitude-longitude systems. So we're going to learn how to deal with different projections, and we're going to learn how to handle datum transformations. Fortunately, it isn't hard to do once you understand what's going on. So we'll learn how to view data in different projections, and we're going to learn how to handle datum transformations. And these are the tools that you use to move data from one latitude-longitude system to another. We're going to see how to project data into new projected coordinate systems, which means to create a brand new version of the data in that new coordinate system. And we'll cover some special issues with raster data. Specifically, we're going to cover the problems that you get when you project raster data, and I'm going to try to convince you to avoid it whenever possible. So what is a projection? In GIS, to project data means to take it from the curved surface of the planet and make it flat. Remember, all data that exists on the planet Earth basically sits on a curved surface. And when we want to put it onto a flat surface like a paper map or a computer monitor, we have to figure out a way to take that curved data and make it flat. Now, there are an infinite number of ways that you can do this, and some of them work better for some purposes than others. The choice of projection can dramatically affect the size, the shape, and the appearance of the landscape. So in this picture of Africa, you see I have it projected using 3 different projections. You see a lot of differences in the sizes and shapes of the countries in Africa. And other projections can have other effects. You can warp them and twist them and orient them in different ways. So a projection makes a big difference in how data looks on the map. The easiest way to project is just to pretend that the latitude and longitude values are the x and y axes on some Cartesian coordinate system, and you get something that looks like this. It's one of the most common projected coordinate systems you'll see. Sometimes it's referred to as the unprojected or the geographic system. Sometimes it actually does have this name, the plate Carré projection. But its only advantage is that it is easy and simple. It's got almost nothing else going for it. This particular coordinate system is famous for being bad about misrepresenting the sizes of things. So you can see Greenland up here looks huge in this map, but it really isn't a very large island. It looks almost as big as Australia, about half the size of Africa, and that is nowhere near reality. Scale on this map is terrible as well. Remember that it's 24,000 miles around the equator, so the scale at the equator is a 24,000 mile line. But the scale at the top and bottom of the map is 0 because that's just a point that's stretched out in the line. There's no distance at all at the poles. Another problem, you miss important and cool information using that coordinate system. Can anybody tell me what is cool and interesting about this line? It is the longest straight line over water. So if you got in your boat, you just headed in a straight line, never turned right or left, just kept on paddling, there is a route you could take that you would travel 19,800 miles over the ocean. It goes from Russia to Pakistan. I love a few things about this route, not just that it covers so much of the globe, but that so carefully threads the needle between South America and Antarctica, and then just sliding in between Africa and Madagascar. It's very surprising that this line could even exist. Okay, let's discuss latitude and longitude coordinates. Most important thing to understand about lat-long units is that they are in degrees, and degrees are angular units, not linear. They describe a position on the curved surface of a sphere or an ellipsoid. This means that they can be measured with a protractor or a compass, but not with a ruler. And the thing to understand about degrees is that they do not correspond with a linear distance. There is no simple conversion between X number of degrees equals so many miles. Latitude and longitude are an entirely different type of system than a linear coordinate system. Latitude and longitude are reported in a few different ways, and I'm sure you've seen these. The one that's most useful mathematically is decimal degrees, and that's a case where you just have a single value for latitude and a single value for longitude. You get the degrees, and then you have a decimal value after that that just does what decimals normally do. They can be reported in a couple of different variations, though. You can have positive and negative values like you see here, latitude and longitude. And remember, negative longitude means it's west from Greenwich, England, usually. Negative latitude obviously means south of the equator. But you can also report these numbers with a letter after it saying whether you're north or south of the equator or east or west of the prime meridian. Now, another common way to report lat-longs is the DMS, or the degrees, minutes, seconds system, and this is probably the most common out there. So we have a single integer value for degrees and minutes, then you often have a decimal value for seconds. Here's an example. You got your 35 degrees, 11 minutes, 24 seconds latitude. You got longitude of negative 111 degrees, 38 minutes, 24 seconds, which is roughly the position of Flagstaff. This one you can also report with either positive or negative values, or you can append an N or S for north or south, or an E or W for east or west. Now, I'll tell you, I'm actually a little confused why DMS is so popular. It's really difficult to work with mathematically. I mean, how do you add 2 degrees values when you got degrees and minutes and seconds? If you got 10 degrees, 37 minutes, 47 seconds, it's hard to just intuitively understand where that fits on the landscape. You got your degrees, and then you got your minutes. You're having to divide minutes by 60 and add that to degrees. And then you got your seconds. You have to divide that by 3,600 of all things and add that to the total. These things are just hard to work with. It's really a difficult and archaic system for reporting coordinates, and yet it's really, really popular. I figured probably the reason it's popular is that it just looks kind of romantic. It's kind of a neat-looking number. It gives you sort of a sense of mystery and magic. But boy, when you actually have to work with those numbers, they're awful. Decimal degrees beats them out in every way. A less common method is degrees decimal minutes. You don't see it too often. In fact, the only place I've ever seen it is in fire reports, where those folks who are sitting up in the fire towers watching for fires, they have historically reported coordinates in degrees decimal minutes. Obviously, this would be an integer for degrees, and then the minutes have a decimal value. I don't know if they still record them this way, but historically they did, and you could really see the effects when you mapped them out. When you rounded it to the decimal minute, you got an interesting effect where the points sort of lined up along a grid pattern. And they also used to just map them to the nearest section, and it may have been as accurate as they could get with those tools that they use up there in the fire towers. The spatial distribution of those old fire points really looks strange and kind of unnatural in the landscape. Another real issue with latitude and longitude is that even though they're both in degrees, they are defined differently. Latitude is defined as an angle up from the equatorial plane, as you see on the left here, and it forms parallels up and down the globe. That's why they call these the parallels of latitude. As you get away from the equator, each circle gets smaller and smaller until it reaches a point at the poles. Longitude, on the other hand, is defined as an angle around a line connecting the North and South Pole. All lines of longitude are actually great circles, and a great circle is what you get when you intersect a sphere with a plane, such that the plane goes through the center of the sphere. In this case, this plane also goes through the poles, the North and South Pole, and a great circle is always the largest circle you can draw on a sphere. Now, we're going to discuss the shape of the planet in a little bit, and it's not exactly a sphere, but the concept still applies. Another cool thing about great circles is that if you follow the line of a great circle, you're actually following the shortest path over a sphere. Now, there's other issues with latitude and longitude that make them difficult to work with. Take a look at this image. All the lines of latitude and longitude are separated by 10 degrees. But notice that if you travel along those lines, if you travel 10 degrees along a line of longitude, you always go the same distance on the surface of the planet. However, if you follow a line of latitude and you go 10 degrees, the distance you actually travel depends on what line of latitude you're at. You travel farther if you're closer to the equator. As you get closer to the poles, though, the distance you travel gets shorter and shorter. Figuring out direction also gets complicated when we're working with latitude-longitude data. A lot of us are sort of used to the idea that if you follow a constant bearing, then that means you travel in a straight line, but that isn't actually true. If you follow a constant bearing far enough over the surface of the planet, you do not go in a straight line. And in fact, if you follow a straight line, this sort of forces you to change your bearing constantly. So take a look at this example. I drew a straight line connecting New York with Moscow. This follows the Great Circle distance, as I mentioned earlier. This means this is your shortest path between the two cities. So as you travel, you would feel like you're going in a straight line. You would not be turning right or left at all. But if you notice, you can kind of estimate the bearing by intersecting this line with the lines of longitude. You can tell that as you leave the city of New York, you're traveling at roughly 35 degrees. And as you get closer and closer to Moscow, your bearing keeps rotating to the right. And when you finally reach Moscow, you're actually traveling at a bearing of 130 degrees. So the bearing that you were traveling changed constantly over the course of your route. Now, I mentioned earlier that following a constant bearing does not take you in a straight line, but there's actually two exceptions to this. One, if you're on the equator going east or west, or if you are anywhere on the planet and going exactly north or south. In both of these situations, you're actually following a great circle path, and therefore you are following a straight line. So, just to recap, the latitude-longitude system is a method by which coordinates are reported in degrees. Degrees are angular units, not linear units. And as such, they make it difficult to work with mathematically. It's tough to calculate distances, calculate directions, calculate areas. The latitude-longitude system is great for reporting the coordinates of a location on the surface of a sphere or an ellipsoid, but they are difficult to work with in most other scenarios. And this leads us to the idea of projections. So, what is a projection? Projection can be thought of placing a light bulb on or near the planet, and you project the features of that planet onto some flat surface. Once they're on that flat surface, then the units are no longer in degrees. They are no longer angular units. Once they're on the flat surface, then everything turns linear. All of a sudden, you can calculate distances, you can calculate areas and directions much easier. So a key difference between latitude, longitude, and projected systems is that the latitude and longitude are angular units, while all projected systems use linear units. Now, there's three broad categories of projection, and these are all based on how you place that flat surface. You can have a conic, planar, or cylindrical. Now, there's an infinite number of derivations of these, but most are based on, or at least are similar to these three broad categories. Now, these are what those categories look like. Got your cone, your cylinder, and a plane. We've all dealt with these before. The common feature between these three is that they are either already a plane, like the plane, or they could be unrolled to be a plane, like the cylinder and the cone. So let's take a look at some examples. Here's a typical conic projection. You see how we've got the projection surface formed into the shape of a cone. We've set it on the planet like a hat, and this is a fairly common scenario. Now, technically, the cones don't have to be oriented such that they're sitting exactly north or south, but this is generally the way you see them. Now, in this slide, I want to show another concept as well, the concept of tangency versus sequency. A tangent projection is one in which the projection surface just touches the surface of the planet, while a secant projection actually intersects the planet. Now, what do you suppose the difference is here? Why would we choose a tangent versus a secant projection? And the answer comes down to distortion, projection distortion. Now remember, we're taking the curved surface of a planet and making it flat, and there's no way you can do that without distorting the surface. And we're going to discuss this more in a second, but the method of projection you choose can give you flexibility over that distortion. You can choose what to distort and what to preserve, but no matter what projection you choose, this distortion is always least where the projection surface touches the planet. So, for example, in this image on the left, the line of tangency, that is where the projection distortion is least. On the right, there's two regions where the distortion is minimized. So why would you choose one over the other? Well, most people would choose the tangent version when they are mapping a small area. And so the map itself will just be kind of centered around that line of intersection, and therefore distortion will be minimized in that small area. But if we're mapping a large region like a continent, then we'll want to use a secant projection where the projection surface intersects at different parts of the continent. Now there will be some projection distortion in between those lines of sequency, but it won't usually be too bad. Distortion is minimized right along those two lines of sequency, and then distortion just gets worse as you get further and further outside of them. And just to be clear regarding tangency and sequency, I'm showing you this example with conic projections, but the concept also applies to planar and cylindrical projections that we'll see here shortly. The key point is that in a tangent projection, the projection surface just touches the planet. In a secant projection, the surface intersects the planet. Okay, moving on. Remember that we use a cone in the first place because it can be unrolled to a flat surface, and this is what that flat surface looks like after you unroll it. Okay, the next class of projections uses a flat projection surface. These are called planar projections. Now, there's three basic types of planar projections based on where you put the light source. Now, it's not critical that you remember the names of these, but just understand the basic concepts. And notice that all planar projections show true direction out from the point of tangency. And remember, the point of tangency is where the projection surface touches the planet. So the gnomonic projection is what you get if you put the light source right in the center of the planet. Projects out, looks like this. I don't know for sure, but I think this may have been one of the original projections, or one of the first projections that were ever developed. I've seen maps from the 1600s that use this gnomonic projection. Now, if we move the light source back to the opposite side of the planet from the point of tangency, they call this the stereographic projection. And then we have the orthographic projection, which is when you put the light source some hypothetical point infinitely far away. All the light rays come in parallel. This orthographic projection is sometimes called the world from space projection because it sort of looks like the planet would look if you were far out in space looking at it through a telescope. It's a good projection for realistic images of the planet. And in fact, I used this orthographic projection in some earlier graphics for this video where I showed the planet rotating for various things. Now, at the beginning of the discussion of planar projections, I said you should pay attention to the fact that all the different flavors of it maintain true direction out from the point of tangency. And by this I mean that if you put a ruler starting at that point of tangency and aimed it at any point in the map, the straight line that connects those 2 points is the true direction from that point of tangency out to that point. So these are basically the great circle paths to get there. Now, true direction does not mean that it maintains a constant compass bearing. We've discussed that earlier. But it does mean it is the true shortest direction, straight line direction to connect those 2 points. And this property is common to all planar projections. Now, the third class of projection uses a cylindrical surface, and this, not surprisingly, is called the cylindrical projection. Now, a quick refresh, tangency versus secancy. A tangent projection is where the projection surface just touches the surface of the planet. Secant projection is when it intersects the planet. And here I want you to see that cylindrical projections, just like conic projections, can have tangent and secant versions. Here's what a cylindrical projection looks like when you unroll the cylinder, or when you view it on your computer screen. It's actually a really common projection. A lot of online mapping services like Google Maps use this projection. Microsoft does, Microsoft Bing, and so do all the Esri web maps. They're all in a cylindrical projection. Now, there's a few different flavors of cylindrical projections based on how you position the cylinder, and really common variations to turn the cylinder sideways. And when you do this, it's called a transverse cylindrical projection. Transverse cylindrical projections look like this when you unroll them. Now, sometimes people orient the cylinder in more unusual ways. When you do this, they call them oblique cylindrical projections. So why do you suppose you'd do this? Can you think of a scenario where you would create or use an oblique cylindrical projection? So the answer has to do with when you have long regions on the landscape you want to map, and these long regions aren't oriented perfectly north-south or east-west. An example might be Baja California, or maybe the Aleutian Islands off of Alaska. These are both fairly long linear features, and if we want to minimize projection distortion as much as possible while using a cylindrical projection, then we might orient the cylinder such that the cylinder touches the planet's surface along these linear regions. Here's what oblique cylindrical projections look like when you unwrap them. Kind of odd looking, and we don't usually use them globally, but they do work really well for those scenarios I described, long linear regions that aren't oriented perfectly north-south or east-west. Okay, quick review. Spatial data start on the curved surface of the planet, and in order to make them flat for a map, we have to project it. There are three broad categories of projection, all based on the shape of the projection surface upon which they are projected. There are cones, planes, and cylinders. Then there are endless variations, all based on how you orient that projection surface against the planet. You can angle them in different ways, and there are both tangent and secant versions, where they either only touch the surface of the planet or they intersect the planet, and so that there are multiple intersection regions. Then there's lots more complex mathematical transformations that are similar conceptually to the cones, planes, and cylinders, but they don't translate perfectly to those concepts. Now, since projections represent the surface after it has been transformed into a flat surface, all of a sudden the coordinates are now linear units instead of angular units. And now we can do all the fun things like calculating distances between points or lengths of polylines, areas of polygons. These things are much easier to do when your coordinates are in a XY Cartesian system rather than in degrees. Okay, I think that's enough for this first video. In the next video, we'll look at several different types of projections, some that are just for fun and some that you'll probably be using quite a bit, like UTM and maybe state plane. We'll also consider why you would choose one projection over another. Now remember that all projections distort, and that's just part of the process, but it turns out that different projections distort different things. Some distort the size and shape of things, others distort distance. And this means that we can preserve certain things. So we can use a projection that preserves the area of a polygon, for example. It might mess up the shape of it, but area can be preserved. And there are other things that can be preserved based on your choice of projection. So we'll look at all that. Then later on, we'll look at datums and datum transformations. These go a step beyond projections. They're pretty interesting and cool, so I look forward to discussing that with you. And then we'll wrap up with a few other special cases. All right, thanks so much.